Now that we've reviewed general information about structure and shape of organic molecules, let's talk about some details of bonding. Our understanding of bonding in organic molecules advanced significantly in the early 1900s due to the theory of electron duality, the idea that electrons have characteristics both of particles and of waves, as well as the Schrödinger equation, which allows us to calculate the energy of an electron. So far, we could use the idea of Lewis structures and bringing together electrons from the Lewis dot model as a type of interaction between electrons as particles. So let's consider hydrogen and imagine taking one hydrogen atom together with another hydrogen atom to form a hydrogen molecule. So on this diagram, we're looking at potential energy increasing in this direction, and this is the internuclear distance. So way out here, our hydrogen atoms are not interacting with each other. They're very far away from each other. As they get closer and closer, they're going to start to interact. And as they interact, the potential energy decreases until it reaches a minimum. So this is the most stable position, and then as those atoms are brought even closer, now the potential energy rises quickly. When atoms interact with each other, we need to think about the fact that there are attractive forces where the positively charged nucleus is attracted to the negatively charged electrons. But there are also repulsive forces where one nucleus is repulsed by another nucleus because they both have positive charge, and where electrons are repulsed by another electron. So as the atoms are brought closer together, there is this combination of attractive and repulsive forces. Early on, it must be that there is an increase in the favorable interactions and not such a problem with the unfavorable interactions. Maybe those electrons can get out of the way of each other. Eventually, we reach the ideal distance, which maximizes the attractive interactions without a problem of the repulsive interactions. But then as the atoms are brought closer together, there's going to be much more unfavorable interactions. So when we consider bonding as interactions between electron particles, then bonding occurs where the atoms are at an ideal distance to maximize the favorable interactions and minimize the unfavorable interactions. And there is a difference. So with hydrogen atoms, this ideal distance is 74 picometers. A carbon-hydrogen bond, this would be 109 picometers. And for a carbon-carbon single bond, the ideal bond distance would be 154 picometers. But now let's think about bonding as interactions between electrons as waves. Well, think about what you've seen in your physics class. If you have a wave and it adds together with another wave, if these waves are in phase, you will have constructive interference and the waves will add. Or if your waves are out of phase, then you will have destructive interference. And those waves will cancel each other out. Well, how does that apply to this diagram? As the atoms are very far away, there's no interaction. As the atoms begin to come closer together, there is some constructive interference and some destructive interference. So the waves are not completely in phase and they're not completely out of phase. And so it's somewhere in between these cases of all constructive or all destructive interference. As the atoms are brought closer and closer, we can think about those waves becoming more in phase until finally at the minimum, the wavelengths are completely in phase, and so we have all constructive interference giving us the lowest energy. As we continue to bring those atoms closer to each other, now we're starting to go back toward destructive interference, and so the energy is going to increase again. So when we think about bonding as interactions between electrons as waves, we're thinking about waves being in phase or out of phase. And bonding occurs where the electron waves have the most constructive interference. So using electrons as waves, there are two different approaches. The first one is the valence bond model. Now, with the valence bond model, we think about having an orbital brought together with another orbital. Keep in mind, we are still talking about hydrogen, so this is a hydrogen 1s orbital of one atom, and this is the hydrogen 1s orbital of a second atom. So these orbitals can overlap with each other. So one orbital overlaps with another orbital. We still have that nucleus in the middle. And then this gives us a new orbital that encompasses both nuclei. So our two orbitals overlap, forming a new orbital. With this new orbital, our electron density is mostly along the axis that joins the two atoms, and so this is called a sigma bond, or sigma. If we could turn this on the side to look at its cross section, let's say this is the back nucleus and this is the front nucleus, then our electron density is going to be like this. So using the valence bond model, the bond occurs when we have orbital overlap. Now these orbitals have to be in phase with each other. When they're in phase and they overlap, it leads to a new orbital that encompasses both nuclei, and the atoms are held together because the electrons are attracted to both nuclei. Before we move on, I wanted to point out something in terms of phase. For some books, they will show one phase as an outline and then the other phase as something filled in. In other books, I guess if they want to use more pretty colors, they would have one phase as one color and the other phase as a different color. So just be aware of these different conventions so that you can tell whether we are talking about orbitals coming together in the same phase or in different phases. Our second approach is the molecular orbital model. So in an atom, electrons are in atomic orbitals, but in molecules, electrons are in molecular orbitals. And molecular orbital theory is based on the linear combination of atomic orbitals to give molecular orbitals. The linear combination of atomic orbitals to give molecular orbitals. In other words, we take our atomic orbitals and we add them together to give us molecular orbitals. There are two options. Our atomic orbitals can be in phase or they can be out of phase. When our atomic orbitals are in phase, they will add together to give a molecular orbital that looks like this. But when our atomic orbitals are out of phase, they will add together to give a molecular orbital that looks more like this. With the linear combination of atomic orbitals to molecular orbitals, there is conservation of number. So because we are starting out with two atomic orbitals, we form two molecular orbitals. When the atomic orbitals are in phase, the resulting molecular orbital is called a bonding molecular orbital, and this is called the sigma molecular orbital. When the atomic orbitals are out of phase, it gives an antibonding molecular orbital. This one is called sigma star. In both cases, if we were to look at the cross section, if this is the front hydrogen nucleus and this is the back hydrogen nucleus, the electron density will still be in a circle. So in both cases, they are sigma orbitals, but this one is bonding because the electron density is along the axis that joins the atoms. And so this will be favorable because the electrons will be attracted to both nuclei. And this one is called antibonding because it has a node. So a node is a region where there is no electron density. Now, when we draw our molecular orbital diagrams, we can think of it as here's our energy increasing in this direction. We write our atomic orbitals on the outside. So this is an atomic orbital, and this one is an atomic orbital. This is a hydrogen 1s, and this is another hydrogen 1s. Each atom has one electron. When we fill in our molecular orbitals in the middle, low energy is our sigma bonding molecular orbital, and higher energy is our sigma star antibonding molecular orbital. Now we consider our molecular orbitals and we fill them up with electrons. We have 2 electrons to work with, and when we're filling molecular orbitals, these obey the same rules as we've seen before. The Aufbau principle, Pauli exclusion principle, Hund's rule. So we have 2 electrons to work with, we fill in our 2 electrons, and we're done. What we see here is that having the atoms together and having those electrons in the molecular orbital is more stable than having those atoms individually. And so bonding occurs because the electrons are more stable in the molecular orbital than in atomic orbitals. We can also use both the valence bond model and the molecular orbital model for p orbitals. Now remember, a p orbital already has a node, but if these are brought together, we can have the orbital overlap. And let's say that these are both in phase, so now our orbitals are overlapped with each other, and so this results in a pi bond. So once again, we have our orbitals that overlap, forming a new orbital. In this case, our cross section, if we were to look at the back nucleus, and let's say this is the front nucleus, then our electron density is going to be above and below the axis that joins those atoms. So very different than what we had in the case of a sigma bond. This one is a pi bond. So if we look at these as our nuclei, with the pi bond, we have electron density above and below, and these are out of phase with each other. And if we look at it from the side, then we see no electron density close to the nuclei, but instead it's above and below. So this is a pi bond. As we consider molecular orbital theory, once again, our atomic orbitals will combine to form molecular orbitals. And so if they are in phase the way that they are currently drawn, then they will add together to give something like this. This would be called the pi molecular orbital, or they could come together like this so that they're out of phase, and that is going to lead to the pi star. So this is the dark phase, and the others are the light phase. Now keep in mind, we want to imagine here's our nucleus. So in the case of our pi bonding orbital, we have electron density above and below. In the case of our pi star, the electron density is also above and below the axis that joins the atoms. But in the pi star, we have another node that goes between the nuclei. So in terms of our energy levels, low energy, we have our pi orbital. High energy, we have our pi star molecular orbital. And if we started out with one electron in each of these p orbitals, we would now have 2 electrons in the pi orbital. So here we see then that pi bonds can be explained either using the valence bond model or the molecular orbital model. So to summarize the models for bonding applied to hydrogen, we're thinking about bonding as interactions between electron waves. And in the case of valence bond model, we think about having the atomic orbitals, which are filled. They overlap and then combine to form the bond. In the case of the molecular orbital model, here we think of the atomic orbitals combine to form molecular orbitals, and then they are filled with the electrons. And you have a bond when those filled molecular orbitals are more stable than the atomic orbitals. It's as if we're thinking about the atomic orbitals are filled and then they combine, or the atomic orbitals combine and then they're filled. So it sounds like we're talking about a difference of timing, but it's more about a difference of perspective. So both of these work just fine for hydrogen. What about when we apply this to larger molecules, and what about when we include pi systems? In both cases, it can be done. Using valence bond model applied to larger molecules, we're really thinking about each bond individually. We can think about the orbitals of one carbon overlapping with the orbitals of another carbon to form a carbon-carbon bond. We can think about the orbitals of, let's say, that second carbon overlapping with a hydrogen to form a carbon-hydrogen bond. And so we can treat each one individually. And that makes it relatively easy. On the other hand, with the molecular orbital model, we really have to consider all of the atomic orbitals combining to form all of the molecular orbitals. And so it does get much more complicated more quickly. When it comes to pi systems, the fact that we can separate out the pi molecular orbitals from the sigma molecular orbitals does make the MO model a little bit easier to use, but still it can be more complicated. So for the most part, we are going to focus on valence bond model because it's a little bit more intuitive, it's a little bit easier to work with, and it's sufficient for many of our applications. But once in a while, we will have to come back to molecular orbital theory for those cases where the valence bond model just doesn't quite cut it.